An embedded system is an ecosystem of isolated microcontrollers, sensors, and motor drivers. For it to function, these components must continuously exchange data. If chip manufacturers did not agree on standardized rules for this data exchange, connecting any two integrated circuits would require engineering bespoke, single-use hardware logic for every single pairing on a circuit board. To solve this, the industry relies on communication protocols. A protocol is a standardized set of physical wiring rules and strict temporal agreements that dictate exactly how binary data is sent, received, and verified. While hundreds of specialized formats exist, 4 mainstream protocols dominate hardware engineering: UART, I2C, SPI, and CAN. Selecting between them is not a matter of software preference, it is a strict architectural trade-off. An engineer must balance the available physical pins on a microcontroller, the need for clock synchronization, and the device's required immunity to electrical noise. Understanding an embedded system means mapping exactly how its architects navigated these physical limitations. The baseline solution for digital communication is UART, or Universal Asynchronous Receiver Transmitter. It is designed for full duplex serial communication strictly between two chips. This diagram shows the minimal hardware requirement for UART. You need a dedicated transmit line routing to the receiver, a receive line routing to the transmitter, and a common ground wire to complete the electrical circuit. The system is asynchronous, meaning there is no shared clock wire to keep the two devices in time with each other. Instead, both devices must be rigidly pre-configured in their firmware to operate at the exact same transmission speed, known as baud rate. In a UART timing diagram, the bus voltage drops to signal a start bit, initiating the timing sequence. The sender then transmits 5 to 9 data bits sequentially. An optional parity bit checks integrity, followed by a stop bit returning the bus high to idle. Because there is no shared clock, environmental noise can easily shift the timing of these signals. If the receiver misses the stop bit at the exact microsecond it expects it, it throws a framing error. If the bit math fails, it throws a parity error. UART works well for simple, direct connections, but dedicating 2 discrete I/O pins per device becomes physically impossible to wire when a single microcontroller must manage dozens of peripheral sensors. Routing a sprawling network of sensors using point-to-point connections requires an unsustainable amount of physical hardware on the main processor. This bus topology illustrates I2C, a multi-master, multi-slave protocol connecting many devices using just 2 shared wires, serial data and serial clock. Because chips can only pull these lines to ground, external pull-up resistors are required to keep the bus high during idle states. Communication begins when a master pulls the data line low while the clock remains high. It then broadcasts a device address to target one specific slave. Following a read-write bit, the targeted slave pulls the data line low to send an acknowledgement bit. This open drain architecture also solves data collisions naturally. Because devices can only pull a line to ground, a master transmitting a 0 will physically overpower a master attempting to let the line float high for a 1. The master sending the 1 monitors the bus voltage. It detects the unexpected low state, recognizes that it lost arbitration, and immediately halts its transmission to let the other master finish. I2C also allows a slave to control the flow of data. If a slave needs more time to process an incoming byte, it will hold the clock line low, a process called clock stretching. This indefinitely pauses the master's transmission until the slave is ready. I2C solves the pin count problem for dense networks. However, the requirement to send addresses before every payload, combined with its half-duplex nature, creates a strict speed bottleneck. When interfacing with heavy payloads like uncompressed audio or SD cards, the half-duplex overhead of I2C chokes the system. The Serial Peripheral Interface, or SPI, is a single-master synchronous protocol. It sacrifices the efficiency of a 2-wire bus to achieve uncompromised full duplex speed. An SPI bus requires a 4-wire topology, a shared clock, a MOSI line for master-out data, and a MISO line for slave-out data. To communicate, the master pulls a specific slave's dedicated chip select line low, allowing simultaneous, continuous streams of full duplex data. This raw throughput requires rigid manual configuration. The developer must program the microcontroller's hardware to match the exact clock polarity and clock phase demanded by the peripheral's datasheet. This illustrates clock polarity, which dictates the idle state of the clock line, either resting low at 0 or high at 1. Clock phase then determines if the receiver captures the data bit exactly on the rising edge or the falling edge of the pulse. If a developer selects phase 1 when the peripheral expects phase 0, the receiver will sample the data line at the wrong moment, and every byte received will be entirely corrupted. SPI provides maximum throughput. It is the optimal choice for high-bandwidth components, trading pin efficiency for dedicated hardware lines and raw speed. Everything discussed so far assumes the clean, controlled environment of a printed circuit board. Automotive chassis and industrial factory floors present an entirely different physical reality. Heavy electromagnetic interference from motors, alternators, and relays easily overwhelms standard 3.3 or 5-volt logic signals. A voltage spike will flip ones to zeros and destroy the data in transit. To survive these environments, engineers use the Controller Area Network, or CAN bus. It is an asynchronous protocol that abandons standard logic voltage entirely, utilizing unshielded twisted pair wires and differential signaling. Instead of a single wire referenced to ground, CAN transmits simultaneously across CAN high and CAN low. For a logic 1, both lines rest exactly at 2.5 volts. For a logic 0, CAN high jumps to 3.5 volts, while CAN low drops to 1.5 volts. This differential math is the core of CAN's resilience. If an external motor induces a massive voltage spike that shifts the baseline of the entire wire bundle by 10 volts, the gap between the two wires remains exactly 2 volts. The data is read perfectly. CAN operates as a pure broadcast system. There are no master or slave devices and no device addresses. Every node on the network reads every message sent across the bus. Arbitration is handled through the message identifier. Because a dominant 0 physically alters the voltage on the bus, it naturally overwrites a recessive 1. If an anti-lock braking module and a climate control unit transmit at the exact same time, the message with the most leading zeros wins the bus. The hardware itself enforces absolute priority for critical safety systems. CAN achieves its reliability in hostile electrical noise by completely redefining the physical definition of a digital bit. Selecting a communication protocol is never an arbitrary choice. It is the fundamental calculus of embedded hardware design. UART provides a straightforward, asynchronous baseline for localized point-to-point connections. I2C drastically minimizes pin counts, allowing a single processor to manage dozens of low-speed sensors across just 2 shared wires. SPI willingly sacrifices those I/O pins, deploying dedicated lines to guarantee blazing full duplex throughput for data-heavy peripherals. And CAN serves as the industrial safeguard, prioritizing electrical immunity and strict message arbitration over standard data framing. To write successful firmware, you must first recognize that the code is entirely subservient to the physical, electrical reality of these 4 protocols.